In today's discussion, I want to begin with a slide that should be somehow familiar to you from the previous chapters when we discuss analysis of variation. The main idea was to partition the variation in a given data set that explains variable of interest, let's say company sales, and we divide the variation in two parts. And because we analyze the difference in variation is presented as sum of squared errors divided by the sample size or the population size, and we analyze the total sum of squared differences. This total sum of squares is usually called in statistics, is presented as or divided in two parts. The sum of squares, which we called explained, and sum of squares, which we called unexplained. The unexplained also referred to as random, which also could be remembered with this name. Today, in this class, in this discussion, we'll add two new terms. The explained part of the variation we'll call sum of squares due to regression, or explained variation with the regression model. The unexplained will remain as unexplained or random or sum of squares due to error. It's the idea is that this is the unexplained or random variation, which is presented here with the sum of square differences, and this is the unexplained portion, which, as we'll see graphically, we can present it in this way, where we have the explained and unexplained and the total variation, the total difference for individual observation. But to understand this, we'll return to the beginning of the presentation and introduce the next statistical analysis. So in analysis of variance, we use the very same idea for one-way analysis of variance or simple ANOVA analysis, when we split the total sum of squares or the total variation in two parts, explained and unexplained part, and the explained part was due to given factor, certain factor. Let's say if this company sales, then the factor could be the our company sales, excuse me, then the factor could be customer demand. And with F criteria, we tested the significance of the portion we assume is explained by this given certain factor. If we want to explain more than one, to add more than one factor, then we must use the more complex and complicated technique, which is similar, but we divide the variation in more than two parts, third part, fourth, and so forth, which is theoretically possible, but practically almost impossible. But behind the simple analysis of variance is the idea that this factor, as a matter of fact, could be presented with the help of a complex multitude or complex range. We can call it one factor, but this is sum of different variables, meaning this factor is presented with many individual variables, factors, which here we can also call predictors, regressors, or again independent variable, as we did in the ANOVA. So the idea behind this general basic fundamental of analysis of variance is that our goal is, if possible, to explain as much as possible from the variation of the data range that explains the variable of interest, let's say the company sales, with the help of one or more factors or one or more independent variables, also referred to as regressors, predictors, and all of them, their total influence will be presented in the group of explained variation. This is the beginning. The next part will be to analyze the individual contribution of each factor, explaining part or portion of the variable of interest variation. And of course, the goal is to identify, to develop, to build such a model which will explain as much as possible from the unknown variation. In this way, the random variation, the error, the unexplained part of the variance will be minimal, very, very small. And after introducing this technique, now let's talk about these two new statistical analyses. In the past, there were two separate analyses, but because both of them require pretty difficult, complex calculations. Today, with the help of even Microsoft Excel, we can get all of them just in a few seconds. And because of this, usually we discuss, we comment, we talk about them as one, correlation and regression analysis, though they have two different goals. The task of the correlation analysis is to identify the strength of the relationship between two or more variables, let's say between sales and customer demand, or between sales, customer demand, company advertising, labor force, and so forth and so forth. The goal of the regression analysis is to build a model, to develop mathematical equation which represents the individual influence or contribution of each individual factor, individual regressor, individual independent variable towards the total explained variation in the variable of interest, company sales. Because of this, at least in the beginning, we'll discuss one at a time, the two analyses, but then when tomorrow, for example, in our lab, we'll perform both of them together simultaneously, because Excel does this in just in a few seconds. So what is the idea of the correlation analysis? Long time ago, in data visualization or statistical presentation, charts, and so forth, we introduce a chart with the name scatter diagram or scatter plot. On this chart, as we can see, we plot two variables, usually the dependent variable, the variable of interest, let's say sales, on the y-axis, and on the x-axis is the factor, the independent variable, the regressor, the predictor. Let's say advertising, cost of advertising, or here advertising in minutes. Why the chart is not a real chart, but just representing dots, the points representing each coordinate or each observation for given level, observation of sales for given level of advertising minutes. The goal is to identify a pattern that could represent the relationship between these two variables. Of course, if we want to analyze the relationship between more than two variables, a scatter diagram is impossible, at least because these are our limited options to present graphically a relationship association between two or more variables. So, what a correlation of the coefficient of correlation or the correlation analysis is looking for? On this chart, we can see different examples of patterns representing different types of relationships. Weak positive relationship, strong negative linear relationship. This one was weak positive linear relationship. These two are relatively strong curvilinear relationships, meaning that we can have many different types of relationships. Of course, with the chart, it's very difficult to identify when a relationship is strong or weak. Of course, there are some ranges. We can say, oh, this looks very, very strong. This looks very, very weak. But to be more precise, after the chart, we need, of course, a statistic. This statistic is known as coefficient of correlation. The correlation coefficient is a measure of the strength of the relationship between two or more variables. In this chapter, we'll concentrate and talk only about relationship between two variables. Next week, we'll expand the case with more variables, that is one dependent and more than one independent variables. The coefficient of correlation, sometimes known as Pearson product moment correlation coefficient, because of the name of the Carl Pearson, one of the statisticians who analyzed for the first time the coefficient of correlation and the correlation analysis. And as we'll see very soon, the coefficient of correlation is based on the standard deviation formula. And because it's a ratio, its value could vary from -1 to +1. -1 when we have negative, very strong, I would say, deterministic relationship. +1 when it is deterministic positive linear relationship. What is deterministic and why did I use this term? Deterministic is a term used in mathematics. When we use a function, for example, when we use the normal distribution curve, all values that lie on the curve represent the normal function, the normal distribution function. Or we can use exponential distribution function, or let's say just the straight line. When all points lie on the straight line, then we call this association or relationship to be deterministic, meaning at any time for given value of the x-axis, we can identify the corresponding y-axis value. Unfortunately, in real-life business, things are not that simple. Meaning the case when we have perfect positive relationship or deterministic positive or negative relationship is very, very rare. Most of the time we deal with stochastic, that this is again from mathematics. In statistics, we call them correlation relationships. What does it mean, correlation? Correlation means that for given value of x, the factor, with certain probability, we can find the corresponding value of the y axis, meaning it's not determined by 100%. And immediately we can make the conclusion, the closer to 1, the coefficient of correlation, the relationship, the higher the probability, meaning when the value of the correlation is 1, positive or negative, it means perfect association, perfect relationship. That is, we, for any given value of factor x variable, we can identify one and only one value of the y-axis. But when the correlation is less than 1, somewhere between negative and positive 1, we can find this relationship with a chance, with a probability. And because of this, we should remember that correlation relationship is stochastic, probabilistic relationship. That is, like any other kind of statistics, we calculate the statistic, we compute confidence intervals, and finally we test a hypothesis about the significance of our calculations, just because this is statistic calculated based on random sample random data. There is no perfect limits or borders, but researchers group the values between 0 and 1 for the coefficient of correlation in 3 groups. Values close to 0, actually, if the correlation is 0, it simply means no relationship at all, no correlation, like this chart. For example, company sales and the number of citizens in Walla Walla. Well, assuming that the sales, the company is not in Walla Walla, it's somewhere else, or something like this. Totally independent variables. And values, usually between 0 and 0.4, are considered to represent very, very weak correlation. Most of the time, it's not worth wasting the time to continue analysis with the next step, the regression analysis. If the variable, the coefficient of variation, the coefficient of correlation represents value of between 0 and 0.4. For 0.4 and 0.7, this is an indicator of moderate, relatively strong association which worth future analysis, at least further test and maybe even a regression analysis. For values above 0.7, between 0.7 and 1, definitely this is strong relationship, strong correlation, and by all means we are on the right track and we must continue analysis with the help of the second step, the regression analysis. Before I continue with something that we know in general, what is the sample statistic, what is the population parameter, I want to make a very important note. Correlation does not imply real relationship. And usually in class, I use an example. Suppose that we have all student grades sorted descending, and all student heights also sorted descending. If we run correlation between these two data ranges, we'll find probably a significant correlation. And we can make conclusion, the taller the student, the higher the student grade. Well, as you can see, there is at least not proven, and there is no evidence in favor of this claim. And this is referred usually as spurious correlation, meaning it's false just due to similarity in data distributions. That is, before performing any correlation, in real-life business, we usually begin with the so-called cause and effect analysis, analyzing, given a certain variable of interest, let's say company sales, the potential factors that the common logic, the business logic, the common sense tell us that may influence the variable of interest, the company sales, like customer demand, company advertising, company labor force, funds, equipment, and so forth and so forth. And then we start correlation analysis. Of course, many researchers say that if there is significant correlation between two variables, by all means, this implies some relationship between them. In general, it's true, but again, by all means, in the beginning, we must perform at least common sense, common business logic analysis of the possible relationship between all variables involved in the case. And then we start analyzing the association, the relationship between the variable of interest, which we usually refer to as dependent variable, and the factors, the independent variables, the predictors, the regressors, many different terms. And again, the statistical estimation or the sample statistics is known as correlation coefficient, and we denote it with the Latin letter ρ. And the population parameter, the population correlation coefficient, is denoted with the Greek letter rho, which is again R. What's the difference? No difference in calculation, just the sign and of course what is behind. Usually the population correlation coefficient is unknown, and with the help of a sample, one or more samples, random statistical samples, of course, we compute coefficient of correlation, and with the help of this coefficient of correlation, we identify the strength of the relationship. And here's some examples how, or approximately how, the chart, the scatter diagram will look for given values of the coefficient of correlation. The calculation here involves sum of squared differences for the two variables. We said we are discussing only the simple case of two variables, one dependent, one independent, and their covariance or mutual, also known as covariation. These calculations are pretty complex and significant, and Karl Pearson substituted for the case of linear relationship with more simple calculations, though as we'll see tomorrow, I'll show you just here the tables. We have all these data, and then we must identify the product moment, the squares, and finally make the calculations. This is the simplified formula of Karl Pearson. Otherwise, it's much more complicated. And of course, as we'll see tomorrow, with the help of Excel will return the coefficient of correlation just in less than a second. But we'll discuss this tomorrow. So what's the next step? Given sample data, we calculate the coefficient of correlation, and then we have to perform the last two steps: the confidence interval and the statistical test of hypothesis. Here, the test of hypothesis is about the significance of the calculated coefficient of correlation. Again, as usual, the null hypothesis is a hypothesis of no significance, meaning the coefficient of correlation is 0, An alternative hypothesis is that no, the unknown population coefficient of correlation is different than 0, meaning the relationship between the two variables is significant. And for this purpose, we use t-statistic and calculate the given, the computed t-value, identify the cutoff point that have two interpretations. First, they identify the confidence interval for the zero hypothesis, the null hypothesis, which of course is insignificant. Why? Because in the middle is 0. And all these intervals represent insignificant coefficient of correlations. And also the second interpretation, second purpose, this is the region of non-rejection, showing that the coefficient is close to 0 and any difference from 0 is due to chance. The other two areas, first, the region of rejection, these are two regions of rejection, and second, these are the values outside the null hypothesis confidence interval. If the calculated t value is within this region, we can reject at the given level of significance, we can reject the null hypothesis, meaning that there is significant correlation. One important note, as you know, the t value, t statistic, is given and identified with the help of the so-called degrees of freedom. And we know from the past, all the previous analysis, that usually we use n-2 degrees of freedom. Now there are n-2. Why n-2? Well, because the first one was the limit due to assumption that the computed arithmetic mean is significant, and n is the sample size. Now, as a matter of fact, as I told you before, and very soon we'll see the, as a matter of fact, I show you in analysis of variance, the real number of degrees of freedom is given by the formula n, sample size, minus k, k is the number of factors, minus 1. This minus 1 we already explained. And because we have a simple correlation analysis, meaning only one predictor, one independent variable, k equals 1. That's why degrees of freedom will be n-1 or n-2 degrees of freedom in total. Next week, we'll see what's happened when we have more than one factor. And here there is one example which we'll discuss tomorrow. But here the example is about the relationship between book price and the number of pages. And from the scatter diagram, we say the relationship is not very close to linear one and doesn't even look as a good relationship. But the coefficient of correlation calculated shows 0.657, meaning that it's a moderate and worth further analysis. Of course, after that, we perform statistical tests of hypotheses, and with degrees of freedom n-2, we identify the computed t-value and make conclusion. And the best, of course, is to find out what is the p-value of the computed t statistic. In this case, it is p-value is 0.077, meaning that we can reject the null hypothesis only if we accept level of significance alpha 7.7%. This is to remind you, one very important property of the p-value, p-criteria, that is, it identifies exactly at which level of significance, we can reject the null hypothesis. That's why p-value is also known as observed level of significance. Okay, so in this case, we cannot reject the null hypothesis. We cannot say that there is no relationship between the number of pages and the price of the book. No, we say that this sample does not provide enough evidence to reject the null hypothesis. And probably this association is due to chance. But we cannot say there is no relationship. We do not accept the null hypothesis. We either reject it or we cannot reject. And when we cannot reject, when we reject it, we say, yes, we can accept the alternative hypothesis, meaning the computed coefficient of correlation is significant. When we cannot reject, we say simply not enough evidence with this given sample data at the accepted level of significance to reject the null hypothesis. All right, suppose that we can accept 7.7% level of significance. Then we continue with the next step. What is the next step? Next step is to analyze the contribution of the factor, or if there are more than one factors, each individual factor contribution. Again, we have one dependent and one or more independent variables, and building, the term most of the time is to build a regression model, is to compute equation. In this case, it will be a straight line, which could be used to explain the impact or the influence of changes that the independent variable cause to the dependent variable, or as general as you see, how much the dependent variable on average changes due to 1 unit change in the factor regressor. But there is not only this. The second goal in regression analysis is, with the help of the computed regression equation, to make predictions, to compute the value for the dependent variable of interest, y, given certain value of the independent variable x. And we start this analysis, but before we start, there are some important assumptions. These assumptions, for example, in this case, is that there is linear relationship between the two variables. There are also some important other assumptions which we'll discuss later on, but they're very important, and if they're not presented, then the results from the regression analysis are not reliable. Okay, what are the initial assumptions? As you can see, besides the linear relationship, we assume that there is logical cause and effect relationship. Both variables are intervally, they are numerical variables, and of course we use a given certain technique known as least squares technique. The idea is to minimize the sum of squared differences, which is exactly, as we know, in the formula for ANOVA analysis. Of course, we can have more than one simple linear relationship. We can have positive, negative linear relationship, but we can have also curvilinear or not linear relationship. Sometimes after computing the regression line, the regression equation, we can find that there is no relationship at all, meaning that the regression model is insignificant. So why starting and wasting the time? Because the skeptic immediately will say, oh yeah, but single straight line, single linear equation is very rare and almost impossible And most of the time it will be insignificant because rarely we can have such a relationship like this one here, very strong negative relationship. Well, it doesn't matter. The idea here is that we can use the simple linear regression model for all explanations. And when we introduce and deal with the multiple regression model, as we'll see, this will be much, much easier to understand. Why? Because here we represent the dependent variable as a function, linear function, of the regressor. As a matter of fact, the first part is just linear component, the straight line. And because we said this is not deterministic but stochastic correlation relationship, we have a second part. The second part is the random error, the unexplained variation. And because we use this component in our equation, there are some assumptions about the errors, which we'll summarize later on, because only in very advanced statistical regression analysis, we use statistical numerical analysis to test these assumptions. Here we'll use charts, and it's very easy with the charts, not even necessary to memorize all these assumptions. We can make all these, or we can test these assumptions graphically, but in a few minutes. So what's happened and what does it mean graphically to develop regression model? It means given sample observations to build a line, a regression line, which represents the linear regression model. And the first component, first coefficient, is the intercept. That is the point at which the line, the regression line, will cross the y-axis. The second, which is the coefficient in front of the factor, is the slope of the line. And because this is the slope of the line, it has very good interpretation, but one step at a time. Next step. When we compute, when we apply the least square technique, we receive computed values, theoretical values, for the dependent variable based on the linear function, linear regression equation. As you can see here, because only linear parts remains, there is no more error component. What happened with the error component? Error component is simply part of the computed values, because computed values contain the real value of the dependent variable, let's say company sales, plus the error. There is no perfect relationship, as we know. Very rarely there'll be perfect relationship. All right, so given this model, how do we use it? First, we said we make interpretation. And the intercept, the B0 coefficient, is simply the estimated y value when x, the x value, is 0. The point at which the line will cross the y-axis. The slope, here, this is the very big power of the linear regression analysis, and further on in multiple linear regression analysis. This is the change, because this is the slope, the tangential, and it shows the expected average change in dependent variable y for 1 unit change of the regressor. So immediately we can use the regression equation to explain the dependent variable y. Second, for given value of x, we can immediately compute or predict the unknown value of the dependent variable y. Let's say x is the customer demand. For given value of customer demand, immediately with the help of the regression equation, we can compute the unknown value of the company sales. Of course, now the calculations are even more complicated than the calculations for the correlation analysis. I'll stop for 1 second, not even a minute, to the formula that we can use to compute the slope. As you can see, it's a function of the correlation coefficient and the standard deviation in the two variables. Now, because the standard deviations are always positive, that means that there is a relationship in the direction between the coefficient of correlation and regression coefficient. Meaning, if the relation is negative and coefficient of correlation will be negative, then the coefficient of correlation also will be negative. How we interpret negative relationship? Well, usually, let's say this is the company sales and the selling price. That is, when we increase most of the time the the selling price, usually the sales decline, and vice versa. When we reduce, which happens very often, especially in time of promotions, Black Friday, Cyber Monday, and so forth, when the prices drop, we reduce the price, the selling price, the company sales increase. And this is example of negative coefficient of regression. Next, we'll have an example which we'll use tomorrow, how to compute, how to interpret each of the coefficients. In general, we already introduced each of them. The point is that when we perform the calculations, there are many statistics in the output which we must use to finish the regression and correlation analysis. As you can see, this is typical output from Excel and other software, which shows the coefficient of correlation, which shows one very important measure, we'll discuss it in a second, shows the ANOVA, analysis of variance, which directly we can use to identify if this factor is significant. That is, in our case, because we use one factor analysis of variance, and this one factor is the regression model, so we can immediately say to identify whether the full model is significant or not. Then we test each coefficient. Because we have only one coefficient here, can you see the p-value for the regression coefficient and the ANOVA significance are the same? Why? There is only one coefficient of correlation, that's why. Okay, and then we can make interpretation, as we just introduced, what is intercept, what is slope, and we can use also this coefficient to make predictions for given value of x. Of course, like for example, if we use the equation about the relationship between book price and the number of pages in a book, so the explanation coefficient of regression shows that each page will cost about a nickel. And if we want to identify how much will cost a book with 800 pages, then we simply substitute x value in the regression equation with 800 pages, and we solve the equation, and then we say that the computed predicted price of a book with 800 pages on average is $89.61. All right, let's return again to the point of the explained, unexplained variable. We said that we applied the knowledge from analysis of variance, and we have two: explained, unexplained variance, and total sum of squares. And the portion, the explained portion, we can measure with the ratio between this explained and unexplained variance. Something similar we use, if you remember, is f value. Yes, but don't hurry. It is f value when we use sum of square due to explained divided by degrees of freedom divided, that is, this is the mean explained error, sum of squared explained, and mean sum of squared unexplained. Here, we simply divide the sum of squares due to regression or explained variation divided by the total variation. Of course, because the total variation is always bigger, then immediately we can say this ratio will be always between 0 and 1. 0, immediately we can say when there is no explained variation, and 1 when all of the total variation is explained by the regression model. This ratio is referred to as coefficient of determination. Now look carefully. Though the coefficient of determination is simply a square of the correlation coefficient, they have totally different purpose. The purpose of the coefficient of correlation is to measure the strength of the relationship between the variables of interest. The purpose of the coefficient of determination is to present the explained value, the explained variation in the variable of interest due to regression or due to regression model, the complex influence of all predictors. And from the output we found when calculated regression model, we can identify immediately this R-squared, which we'll do tomorrow in our example, and we can test the significance of each coefficient, the R-squared, the coefficient of correlation if we want, the ANOVA test, the individual test, to compute with the help of the standard error. This is the standard error of the estimation, which we can calculate as a sum of squared unexplained variation divided by the total degrees of freedom. And as we know directly, though it looks that we can use it as you know, standard deviation cannot be used directly. We use it how? Using the empirical rule to compute the confidence intervals. Then we have here another example that we run regression, we test then coefficients, and we reject or we do not reject these coefficients, this hypothesis based on the significance of the coefficient. Then we compute confidence intervals, also known as prediction intervals. Finally, everything we'll do tomorrow. Finally, let's return to the point in the last couple of minutes. The point of the reliability of the results obtained. What does it mean? It means that we made some assumptions in the beginning of the correlation and the regression analysis. And we must test this, which is known as testing the aptness of the model, or also residual analysis. Residuals is another term or another name of the errors, the differences between computed values with the help of the regression equation and the real observations. What is the goal? As I told you, there are different assumptions. We are not calling each of them because our goal is mainly to identify or to show a chart. What is the chart? Do you remember that we can use? For example, if we want to plot the distribution, we'll use scatter plot. We can use either histogram or box plot. Why? Because we have to test if the residuals are normally distributed, one assumption in regression analysis. If not, like this case with the book pages and price of the book, and apparently the assumption of normality or normal distribution of the errors is violated. Second, we must draw a chart representing a scatter plot between residuals and the regressor. If more than one, there'll be a regressor, then will be more than one chart. What is the goal? The goal is here to find a totally random scatter plot. Otherwise, Let me show you some example. If there is a pattern, well, if there is a pattern, we can look and find what kind of pattern is this. Sometimes if non-linear and we assume linear relationship, then apparently we cannot perform linear regression and correlation analysis. What else? Sometimes we are looking another very, very important, which we introduce in analysis of a variance, that we expect a constant variance in the dependent variable. Here we expect constant variance in the residuals. Otherwise, what's happened? Otherwise, it means that the larger the X value in the predictions, the larger the variance, which will make the confidence interval, which happened, by the way, we'll discuss it tomorrow, bigger and bigger. Well, it's expected because the confidence interval is non-linear function, but there are some natural limits in this confidence interval based on the total random expectations in the errors. When this is not random, but they're significant, then we have non-constant variance. Just a joke in the past, because the term here is homoscedasticity. And I offer in class extra bonus point if students can memorize this term. It's a Latin word meaning equal variance. And even I gave this at exam time, and I remember a student who wrote in the final part, there is usually in the final exam, I give extra question for extra points, and he wrote, I don't remember this question, but I memorized and can spell homoscedasticity. And of course, I gave the student extra point for this. Good. So this is the final step in regression and correlation analysis, to test the assumptions. If these assumptions are violated, then the results are not reliable. And with this, I will stop recording of today's presentation.